Uh, I want to present to you a topic of cells and simple circuits, which is a topic on current electricity 1. You will meet with current electricity 2 in Form 3. This one is just but as simple as cells used to form a simple circuits to simply light a bulb or a radio or a torch. Now, what is there here is at the end of this topic again, we will have supposed to have achieved the following objectives. First one, draw and set up a simple electric circuits, identify circuit symbols, define electric current, explain the working of a primary and a secondary cells, explain the care and maintenance of secondary cells. So now, let's start. Electrical energy has many uses, and it can be converted into other useful forms. For example, light, heat, and operating other devices in our homes and offices. Right now, you can see me clearly because there is a light in my room. You can cook using a heater simply because it can convert electrical energy to heat. I'm using my computer to present to you a lesson simply because the electrical energy in the wires can be converted to something useful. That is it. First of all, let's start by looking at what is electric current. What is electric current? Electric current is the rate of flow of charge. It is the rate of flow of charge. Whenever you see the word rate, a time is involved. And when a time is involved, then we can, define this term that it is a flow of charge per unit time. So there are two things I want us to know about current. Current is a physical quantity. Therefore, it must have units. And this current, the first thing I want us to know, what are the units of current? The units of current, or the SI unit, is ampere. I'm becoming specific, ampere, because it can also be measured in milliampere. Simply because sometimes the current is too small, so we record it in milliamperes using milliammeter. If you want to measure current, we use a ammeter. It gives you in amperes. But now, if you want to get it in the smallest units of current, then you will use a milliammeter that gives you in milliamperes. But the SI unit is ampere, and ampere is denoted by letter A. Now that's where I want you to be very, very much keen. The other thing is, electric current has its own symbol. Current is denoted by letter capital I. So whenever you see I, that is current. Some of you goes ahead and they confuse and they say that current is denoted by A. Please don't confuse. A is for ampere, the SI unit to current, and I is for current. Now, from our definition, that the current is the rate of flow of charge, or flow of charge per unit time, then it means for us to get current, we must have charge. Charge is denoted by letter Q. And because we have said per unit time, then we have to divide charge with time. And this time should be in the SI unit. Can you remind yourself what was said to be the SI unit of time? It is seconds. So when you have time in seconds and charge in coulombs, we learned this in electrostatics 1. Charge is measured in coulombs. Then when you divide charge in coulombs over time in seconds, you will get current in amperes. So that's why I'm giving you this particular equation here, that current is given by charge over time. Charge should be in coulombs, and time should be in seconds. So whenever you are given time in minutes or hours, please go ahead and convert it to the SI unit. Even when you are given charge in other units, please go ahead and give it in the SI unit. And I've been saying all this through in my presentation, that anytime you are carrying out a calculation question in physics, please ensure that the quantities you are dealing with are in their SI unit. Please do that. Now in this case, to avoid a lot of writings, current I will use I, charge I will use Q, and time I will use T. So I, as per our definition, is Q over T. Q is IT, and T is Q over I. So using one formula, that I is equals to Q over T, you can get the formula for calculating charge and even time. You can look at an example. Calculate the amount of current flowing through a bulb if 360 coulombs of charge flows through it in 3.5 minutes. In 3.5 minutes. So first of all, look at the question. It wants us to calculate the current. So current is given by Q over T. That's the first formula. Write that formula. I will give you a mark. Every teacher will give you a mark on the formula. And then from there, now let's replace. Let's substitute. Q, we have been told 360 coulombs. Nice. But now here, time is given in minutes, so we have to convert it in seconds. So 3.5 multiply with 60. There are some of you who don't know that 1 minute is made up of 60 seconds. They don't know that, but let me make you know it. So 360 over 3.5 times 60, you will get 1.714. If you are also very keen, you can get many other figures, but what I've given there is 4 significant figures. I'm saying 4 significant figures. Don't give 2 at 1.7. No, you will fail. Or 1.72. No, just give into 4. You will be safe when you put it in 4 significant figures. No one will punish you if you give 10. I mean, more than 4, no problem. But less than 4, there's a problem. Unless you have used your calculator and it gives you exactly 1.71, there's no problem with that. Or 1.7, there's no problem with that. Another one, I will give another one example as we are moving on. So now this type of this current that we are dealing with, because it's the main thing we are studying it here, they are categorized into 2. We have direct current, we call it DC. When you see DC in physics, it is not district commissioner, it is direct current. We also have what we call alternating current. This is not assistant chief, it is a current that alternates. Now, I will explain to you. A direct current is the one that flows in one direction only. You see, in a wire or a conductor that allows current to pass through, the current can decide to be flowing in a reverse direction under a given frequency. That one will be alternating current now. But if it can flow in one direction only, then we call it direct current. But if it flows with reverse direction under a given frequency or in a given time, then it is alternating current. Apart from flowing in reverse direction and flowing in a straight line, the other difference between direct current and alternating current is being steady. Direct current is steady, meaning if it is 2 amperes, all through it is 2 amperes. But alternating current, sometimes it can be 2 amperes. At a point it goes down almost to 0, or it goes up to 3 amperes. So you see, it is not steady. And it is not safe for us to work with alternating current. Though there are electrical devices that can work well with alternating current. For example, bulbs, the one that are pointing at me up here, they can use alternating current. They can use. But the computer I'm using right now will not work well with alternating current. It will be going on, off, on, off. If you are very keen, it's only those who are keen. If you are not, then if you have never seen what I want to explain, then categorize yourself as people who are not keen in this country. At some point, a bulb lights brightly. In a very short period of time, it goes dim, bright again. But I'm talking to those who are keen. Then it's because the current keeps on deviating from 2 amperes, 1 ampere, less. Sometimes even it goes almost zero. Then it's like the bulb wants to go off. That is it. So we have two types of electric current: direct current and alternating current. You guys are being taught here. When we are in Form 3, we try again to tell you what is direct current. You are just without a clue. Anyway, let's look at the simple electric circuits. It's just as simple as the name. It consists a cell, a bulb, and connecting wires. Given a cell, a bulb, and connecting wires, you are supposed to make that bulb light. If you cannot, then anyway, this is an example of a simple electric circuit. Just look at it. It as a dry cell here, or simply a cell, a bulb, then connecting wires. Go to your lab, ask your lab technician to give you some wires. Dry cell, a bulb, try to connect until it lights. But after that, don't feel like you are an engineer, electrician. No, you are just but a student. Now, the first note is this: a circuit that allows charges to move in a complete path when the switch is closed is said to be closed circuit. It is closed, meaning it is forming a complete path. A circuit that does not allow charges to move in a complete path, such a circuit is said to be open or broken circuit. This reminds me of my biology back then. We have two types of circulatory system: closed and open. Now this one is closed circuit, not circulatory system. Then we have open or the broken. Broken does not allow current to flow through. Open circuit can also be as a result of loose connecting wires. So whenever you are connecting this, ensure the wires are very good. Sometimes the bulb may not light simply because the wires are not continuous. You know that they are insulated and you cannot see the inside the wires, that whether they are complete or not. Some of them, the protruding wire, that is the naked wire from one side, are not continuous to the other side. So sometimes don't blame yourself so much. Maybe it is the wires, but in most cases, it is you. For clarity and neatness, symbols are used. Symbols, not SI, it is SYM. Symbols are used. This one are used in representing an electrical circuit. Yes, this one is a switch. So you see now we are drawing them to be straight. When you connect, the wires will not be straight as my diagram here. But when drawing, this is for neatness and clarity. Even if you are not used to being neat in daily life, please ensure the diagrams in simple circuits are neat against your will. So you see, now there are things here I want to explain to you. Please listen to me. This is a cell, and this is a symbol of a cell. I will still show you other symbols here, but this is a symbol of a cell. Okay, let me just show you first, then we go back. I will explain something to you. Cell has two terminals, a longer terminal and a shorter terminal. The longer one is positive. You know, a cell must have a positive terminal and a negative terminal. That one is for everybody to know. Whether you are in class 6, class 5, a cell has a positive terminal and a negative terminal. So using our symbols, the shorter one is negative. The longer one is positive. So that's what you need to know. There's a difference between a cell and a petri. Several cells makes up a petri. Several cells makes up a... When you see more than one cell, that's not a cell, it's a petri. That's why here, in our second case, it's a petri made out of several cells. Don't keep on writing here negative, positive. No, just at the end positive, and then the other side at the end it is negative. A switch is it of this way so that you can easily close it. Then a bulb or a filament has two symbols, a cross like this, or the one having a symbol of a filament. Then when we proceed higher in our current electricity too, we will be connecting using very many wires because we are going to engage many electrical appliances. So at some point wires will cross each other, and then we have two wires crossing. So it can either be the wires are crossing with no connection, ni kama sile barabara, another one is going to do, down, you know, we have a flyover, another one is going through up the flyover without any connection. Even if you want to use the lower road, you will have to go and maybe connect from somewhere else. Then we have those roads, the ones we have at home. They cross each other with connection. So when the wires are having connection, meaning a current flowing from here can easily divert to the other type of to the other wire. So when they have connection, you shade to show those wires are crossing with connection. This one is without connection. There are things that we shall use later on in our next topic. Fixed resistor, potential divider. Potential divider is can say to be variable resistor. Yes. We have a fuse. Fuse has two symbols, this one and this one. Capacitor, but we will use it in electrostatics too, don't worry. Rheostat. Rheostat can still function as a variable resistor. Ammeter, voltmeter, and galvanometer. I can say something small concerning the ammeter, voltmeter, and galvanometer. Ammeter is used to measure current in amperes. Voltmeter is used to measure voltage in volts. Galvanometer is used to show the presence of a current in a conductor. Yes, so that is it. Now, I wanted to explain something here. You can see a cell here. We have a positive and we have a negative terminal, and then the current has to flow. So my point is this: the current always flows from the positive terminal this way towards the bulb, then it will enter the cell again through the negative terminal. Get this statement, it will confuse you, but just get it. For current to flow, electrons must flow. And when electrons are flowing, current is flowing. They flow in opposite directions. Electrons are flowing from the negative terminal of the cell in this manner. Current is flowing from the positive terminal of the cell in this direction. So those are the two. If there are no electrons flowing, there is no current flowing. They are flowing in opposite direction. Again, we call it in biology or in science counter current flow. Anyway, it's well. So that is it. Get it very well. When the switch is open, the bulb will not light. When using voltmeter, we can measure voltage in two ways. We can measure voltage in two ways, and then we obtain what we call electromotive force or potential difference. Electromotive force is shortened as EMF. Potential difference is shortened as PD. All of them are voltage, but measured under different circumstances. Let's see. What is EMF? Or at what time can we say this voltage is EMF and this voltage is potential difference, that is PD. When you measure the voltage of a cell that is not supplying any current, it is not being used to maybe light a bulb, it is not used to maybe start, light a torch, then the voltage will be higher, and we refer to it as the electromotive force. It refers to the voltage across the terminals of a battery in an open circuit. That is, when no current flows in the circuit. But when the cell is used to light a bulb or is functioning to light a bulb, and then you measure its voltage when it is functioning, you will get a lower voltage simply because some of it is being used to drive the current. Now, that one would be called the potential difference. It refers to the voltage uh, across the terminals of a battery in a closed circuit. Closed circuit when current is flowing in the circuit. All of them are measured in volts, and they used a voltmeter as I have said earlier. Yes, I think I said that. So now, I said EMF is higher than potential difference. EMF is higher than PD. The difference between EMF and PD is lost voltage. It can be lost in two ways. Because when it is being used to make a current flow through a conductor, this one you will learn it in future. A conductor has resistance that does not allow the current to flow, but the cell or the battery will work against that. That's why some of it will be used to make the current flow. And when the current flows now, the EMF drops, and now it becomes PD. Hope you're getting me. Cells, there are two connections here that we can connect cells to give a battery. We call it series and parallel. Let me start with cells in series. Cells in series, or cells can say to be connected in series, when the negative terminal of one cell is connected to the positive terminal of the other cell. If you follow up like this one, this is negative. Okay, here we have two cells. We have negative terminal connected to the positive terminal of the next cell. So it is a series connection. But if I connect negative to negative of another cell, it becomes parallel connection. We always connect cells in series to increase EMF and hence increase the current flowing through that particular circuit. When you connect cells in parallel, like this one, you see now the positive goes to the positive, the negative goes to the negative. This is a parallel connection. It gives a lower EMF. That is now the disadvantage of connecting cells in parallel. It gives a lower EMF. It's just like that of one cell. Even if you connect 100 cells and then you measure the EMF, it just gives you 1.5 if you're dealing with a cell of 1.5 volts. So it is a disadvantage. But if there's an advantage, it's because it will serve for a longer time. But that's not too much to overcome the disadvantage that it has a lower EMF. So again, when you connect two dry cells of a different EMF, one will drain the other. One will take the voltage from the other one. So cells should only be connected in parallel if they have the same EMF. If they have the same EMF. So always, cells should be connected in series. Yes. Now look at these bulbs, in series and in parallel. Before I move on, I said cells should always be connected in series. In bulbs, it is opposite. Bulbs should always be connected in parallel. You will get the reason as I'm explaining something here. The bulbs you are seeing here are in parallel. And they bend on a cell somewhere here. Maybe or a battery. And for a bulb to function, there must be a complete circuit. These three, even if one bulb is removed or damaged, the rest will still work. But in series like this one, when this bulb goes off, the other will not function, because for current to reach this other bulb, it must go through the damaged one, and hence there will be no complete circuit over there. So cells, bulbs should be connected in parallel. Because if one goes off, the rest will work independently. Yes. So even in the street lights, they are always connected in parallel, because you will find some bulbs not working, yet the others are working. So if they were in series, then when one goes off, the whole street, no lights. Yes. So know when bulbs are said to be in parallel like this one, and know when bulbs are said to be in series like this. Even these cells are also in series. Yes, look at this particular simple circuit. An electrician installed electric wiring in a house and connected bulbs and the switches as shown in the figure below. We have the kitchen bulb, the sitting room bulb, the bedroom bulb. We have switch 1, 2, and 3 named as S1, S2, and S3 respectively. So they're asking you explain what happens when switch 1 is closed. When you close switch 1, let's look here. When you close this switch here, yes, it's only bulb 1 that will have a complete flow of current. Bulb 2 and 3 will not light. So only bulb 1 will light. When S2 is closed, and the rest of the S, that is the switches, are open, because the current will flow this way, so bulb 1 and bulb 2 will light. Bulb 1 and bulb 2 will light. When we close S3, all the bulbs will light. All the bulbs will light. But not with the same, not with the brightness that S1, bulb 1 was lighting when only S1 was on. When you complete S1, bulb 1 will light brightly. When you complete S2, you know, the two of them, B1 and B2, will light, but with less brightness right now because they are sharing. When you include S3, all of them will light, but the brightness will go down. You hear me? Yes. There's something here. Using these ones. There's we have the kitchen, the sitting room, and the bedroom. So here the bulbs were in series, which is against what we know. So when you are told now to redraw, you take this bulb here, take this bulb to be here, take this other one to be here. Now to be in parallel. Or okay, after taking B1 this side, take B2 here, then B3 can remain there because it's just now all of them are in parallel. And when one goes off, the rest will still function. They will function independently. Yes. Let me, there are three materials here I want you to know. We have conductors, semiconductors, and insulators. Conductors allow current to flow. Insulators do not. But a material whose electrical properties fall between those of our conductors and insulators are said to be semiconductors. For example, silicon and germanium. Not only liquids, but also some, not only solids, but also some liquids can allow current to flow. For example, dilute sulfuric acid, sodium hydroxide, sodium chloride solution, potassium hydroxide, even sodium hydroxide as well, it conducts electricity. So a liquid that allows current to flow through, we call it electrolyte. Yes. Now, we have been talking about electricity. Now, we have three main sources of electricity: chemical, cells, generators, and solar cells. But in our case, we will only talk about chemical cells. Generators and solar cells, we will talk on later on. So, this is Ambassador Foundation YouTube channel. I welcome you. Follow my lessons for physics and chemistry. Subscribe and share it widely. God bless you.